So my name is Ken Grattan, and it's my honour and my privilege to be the George Daniels Professor of Scientific Instrumentation here at City University of London, and to give you a very warm welcome to the lecture tonight. I can see we have a full house, so that's really, really good. With a full house, however, I think the housekeeping announcement is slightly more important. There are no fire alarms expected tonight, but if there is a fire alarm which sounds, then we need to muster in Northampton Square, and there are some city people here who will be, no doubt, leading the way out and making sure that they get out, so follow them and you should be fine. And also, could I ask just to do what I'm just done, and that is put my phone onto silent. Okay, so my role here at City is one which I see follows on, I think, very naturally from the work of George Daniels in his own specific field of instrumentation, and reflects his foresight and his generosity to the university in many different ways. The George Daniels Undergraduate Scholarship are supported by the George Daniels Educational Trust under the chairmanship of Mr. David Newman. And they were established by Dr. George Daniels, who was past master of the Worshipful Company of Clockmakers, and it's a delight to introduce a number of the, to welcome a number of the clockmakers here tonight, to honour the scientific legacy of Dr. Daniels, who was an alumnus here at City. And we are delighted that the Trust has been able to support a number of undergraduate students on an annual basis, and there are a number of them in the audience with us tonight. For those of you who are less familiar, George Daniels was considered to be the best in the world during his lifetime as one of the few modern watchmakers who built complete watches, and that included the case and the dial, and did that by hand. And his creation of the co-axial escapement is really the aspect for which he is the best remembered. And I think the quality and the rarity, really, of what he has done is seen in the fact that his yellow gold chronograph pocket watch, the Space Traveler's Watch 1, ranks as one of the most expensive watches ever sold, fetching almost £4 million at auction fairly recently. So with that legacy, it's an absolute delight to introduce our speaker this evening, Dr. Roger Smith, who's going to talk about the development of the mechanical wristwatch. Roger Smith's horological career began at the age of 16 at the Manchester School of Horology, where he passed out top of the class with the British Horological Institute's bronze medal. And it was a visit from Dr. George Daniels which inspired Roger to take up the ambition to hand-make watches. And so about 30 years ago, he started making watches, and today is Britain's most highly regarded watchmaker. And he will discuss in his lecture, as you can see from the title, Developments in Modern Mechanical Wristwatches, and share something of his own observations in the field. But Roger established his own studio in the Isle of Man in 2001, after working alongside Dr. Daniels to create the Millennium Series of watches, and the seminal Millennium Series 2 was produced in 2006. You will not be surprised to know that Roger's distinction in the field has been particularly recognized by his peers. In 2012, the British Horological Institute awarded Roger the Barrett Silver Medal in recognition of his dedication to continuing the finest traditions of English watchmaking. And in 2013, he was invited by the Prime Minister's office to become an ambassador for the Great Britain campaign, representing the best of British innovation. And that led to a now iconic series of watches, the Great Britain watch. I think perhaps just to finish the introduction, the distinction that Roger has had in the field was recognized in 2018 by Roger being made an officer of the Order of the British Empire for outstanding services to watchmaking. And this year, Birmingham City University awarded Roger an honorary degree, an honorary doctorate, in recognition of his achievements in horology. So, with that background and with that introduction, it gives me very great pleasure to call upon Dr. Roger Smith to present this year's George Daniels Annual Lecture.
Thank you very much, Ken, for your very kind introduction. Well, first things first, we're on time, which means the rest of this lecture should be a home run. Today, I'm going to talk to you about a problem, a big problem, with, or rather in, modern mechanical watches. It's a problem most of us probably don't know we have. But fear not, I'm also going to talk about my solution. Now let's be honest. Coming to this lecture to get the solution to a problem you didn't even know you had when you arrived, well, that might not sound like a productive evening. But please stay with me on this. Most stories about watchmakers and their discoveries are about obsession. We are obsessive people. My own watchmaking career has been an obsession which began over 30 years ago. Since that time, I've designed and built 101.75 British watches. Yes, I do keep count. I've also been proud to achieve several genuine firsts for our resurgent British watchmaking sector. And along the way, I've had moments which changed my way of thinking. In fact, one of my earliest epiphanies was during my early 20s, but it would influence everything I have done since. And it leads us ultimately to that aforementioned big problem. For now, though, let's dial back and set the scene. It's 1990. Around the world, it's a time of huge change. Germany has just been reunified. Nelson Mandela has walked free. The Hubble telescope has also been launched, giving us a deeper view of our universe. But arguably, the most profound development for ordinary people, Tim Berners-Lee, has created the first web server, and with it, the foundation of the World Wide Web. And although in 1990, my world was very humble by comparison, for a horologist, it was also multifaceted. By day, I was restoring vintage English pocket watches, and I was servicing modern mechanical wristwatches. By night, I was hand-building my first and second pocket watches. Now, on a daily basis, while restoring those vintage watches, I gained an insight into several centuries of development of the mechanical timekeeper. Alongside the experiences gained from making my first two pocket watches, I soon realised something. These old pocket watches that I was restoring, made in the golden age of English horology, they were spectacular. These watches were built as strong as castles, for one thing, but married that robustness to high-quality finish and insightful design ethics. How different, then, to the modern mechanical wristwatches I was servicing. From their initial conception, these modern watches were low-cost, mass-produced, and built with a limited lifespan. Then, marketed as luxury. Now, dialing forward, I like to jump off at 1998. It's now 6 months since I completed my second pocket watch, and I have moved to the Isle of Man to work with Dr. George Daniels. This is when I went from being inspired by to becoming fully immersed in George's unique world. Now, he was a horologist with an innate and masterful understanding of the escapement, of mechanical watch design, and of construction. As I became immersed, so my earlier experiences with those wonderful English pocket watches were mixed into this new formula. I began to form my own ideas on how I might improve upon the life of the modern mechanical wristwatch. And so we get to today, right now, to the big problem and the point of where this has taken me. Here's the problem. We accept an industry standard for service intervals of between 3 to 5 years. Okay, some are a tad longer, but typically it's 3 to 5 years. Really? That's our standard? Compared to those pocket watches of centuries past, well, frankly, I find that rather shameful. I mentioned Tim Berners-Lee earlier. Imagine if he'd started out with broadband in 1990, and today our industry standard is a 28K modem. Well, it's amazing what we accept when that's the accepted standard. So tonight I'm going to look at the watch as a whole, as a watchmaker, rather than the sum of its parts, as dare I say it, a watch assembler. I'm going to talk to you about how we can practically solve this problem. And that's our theme this evening. The development of the mechanical wristwatch. As I have already alluded, I believe the modern mechanical wristwatch is not in a healthy state. It's always interesting and contextual to draw comparisons with other industries. And let's face it, cars and watches have long been bedfellows of our enthusiasm. And I'm always grateful to the car industry. Why? Well, think about it. Collectors buy both cars and watches, but it's cars that bear the brunt of the midlife crisis, and I should know. I like to think this is why we don't have Russell Red Rolexes. That said, my earlier experiences of cars were not always happy. Life with a car some 30-odd years ago was a constant struggle to stay road legal and running, while staving off the eventual demise of a now rusting lump of metal. Today, huge leaps have been made in terms of car safety, reliability, performance, longevity, and most important today, energy efficiencies. The cheapest cars today offer guarantees and warranties on all those aspects which would have put the luxury marks of 30 years ago to shame. That's in just 30 years. And there has been a non-stop evolution in the short century plus of the combustion engined car. Now let's look at the mechanical watch. Well, to start with, let's not forget that we've got centuries head start on automotive. When the pocket watches that captured my imagination were being made in the 18th century, horsepower meant just that, horses. Yet, in my opinion, the efficiency of the mechanical watch has stood still. and in many cases it has regressed since the 1950s and 60s. And this despite many purported technical advancements and the introduction of new wonder materials to our tool chest. So what is my own litmus test? Very simply, it's the service intervals of watches. Throughout my years at the bench, service intervals have remained static and have even declined since the mid-20th century. Back to our automotive context. Imagine leaving here this evening to drive home in your Morris Minor. Now, there have been attempts to improve the accuracy of the watch. We had a period of great invention and creativity in the 1960s and 70s, but with the development of the quartz watch. Quartz was to revolutionise the Swiss watch industry with its super accurate timekeeping. And it did. But the casualty was the art and the science of mechanical timekeeping. A deep well of knowledge was lost. In my view, the quartz watch lacked soul. In the immortal words of George Daniels, at the least opportune moment, the battery will commit suicide without warning. Ironically, whereas electric is posited as a saviour of the environment in our parallel automotive world, in watchmaking, it's the opposite. Quartz generates waste. There is nothing more environmentally friendly than a watch powered by human movement. In this respect, mechanical really is superior. In any case, the quartz watch simply did not capture the hearts and minds of the public. Lacking the soul I mentioned earlier, quartz was a race to the bottom for product value. Timekeeping as utility rather than pleasure. And for the luxury sector, utility is the enemy of value. And so the baton was passed back to the makers of mechanical watches. But the mechanical watchmakers now had a problem because society had become used to these new timekeeping standards. Quartz might be soulless, but it kept undeniably great time. And now we were surrounded by accurate timekeeping on TVs, cookers, computers, and more latterly, phones. It would be a pretty savage irony for the one object designed to tell the time to be the least capable of doing so. And so the accuracy of the mechanical watch had to improve in order to meet with the elevated expectations of the customer. The industry needed to rethink, and the answer seemed to come in the form of the fast beat watches. The idea was this. You take a standard watch, which ticks at 18,000 vibrations or beats per hour, and increase the number of ticks that it does per hour. By squeezing extra ticks into each second, you average out the errors across each tick. Development of fast-beat watches had begun in the 1960s, but was hampered due to the poor quality lubricants of the day. The industry responded, and better quality lubricants were developed to cope with the higher frictional demands of these high beat frequencies. Lo and behold, the theory of squeezing more ticks into each second appeared to work, with improvements in timekeeping. But there was a dark side to this equation. Due to the increased friction, the working life of the lubricant was now shortened, and this led to a reduced service interval for the watch. And here is a graph which explains why. The green line shows a number of ticks in millions that a watch with an 18,000 train will achieve over a 10-year period. 157,680,000 vibrations per year. And the yellow line represents the number of ticks that a 28,800 train will achieve over the same period. 252,288,000 vibrations per year. This equates to the fast-beat watch having to tick an extra 94,608,000 ticks per year. That is a huge amount of extra work demanded of this micro machine. What is interesting is that after 6¼ years, the fast-beat watch will have performed as many vibrations as the low-beat watch does in 10 years. But the concept is once again perhaps best experienced in our automotive parallel. Simply this. Imagine driving your car on the motorway, flat out in third gear. And this is another problem. The fast-beat watches are working too hard, and the mechanism behind the escapement and its lubrication is not up to the job. This is why service intervals have been shortening, which in my view is a backward step for watchmaking. So how do you improve the performance of a mechanical watch? First of all, you look at developing an escapement which will maintain a good rate of timekeeping over a long period of time without attention. It must be practical in every sense of the word. This is where George Daniels was a true pioneer. He could see that after 250 years of development, the commonly used lever escapement had reached its zenith. No amount of tinkering with new lubricants or higher vibrations could improve on its life. Instead, a radical rethink was needed. To date, the resulting co-axial is the only new escapement which can claim to be practical. Now, what do I mean by practical? I have put it in capital letters here in my speech, so it must be important. Well, it means it is. It is robust in construction, mass-producible, simple to set up. Finally, it means it can be scaled down to fit all sizes of caliber. The next stage is to design a mechanism which is capable of housing this practical escapement. And as with the escapement, the mechanism must be very strong and able to run without attention for long periods of time. I'd just like to sidebar with an explanation of what an escapement does for non-horologists, but also for horologists, since it does no harm to get back to first principles from time to time. An escapement in mechanics is a device that permits controlled motion, usually in steps. In a watch, it's a mechanism that controls the transfer of energy from the power source to the counting mechanism. So it plays a crucial role in keeping time. Having spent the past 30 years studying, developing and making escapements, I have found there are some basic rules which must be followed when you design a practical watch escapement. It's such an in-depth subject, I am going to discuss one area of the escapements. But it's an important one in arriving at our solution. It's how the power and impulse is transferred up to and through the escapement. And the reason for me focusing on this area is that this is where my practical experiences have led my escapement work. However, before I move on, I would encourage any of you with an interest in escapements to refer to this book by George Daniels. This is the study of the development of an escapement from a hands-on, practical approach. There is no better book on escapements, and throughout, George analyses the pros and cons of all the major escapements throughout history. He then focuses on the development of his own escapements. On a personal note, having seen many new escapements coming to market over the past 10 to 15 years, it does surprise me how little attention the industry pays to this great work. Anyhow, before I move on, I must remind us of practicality in escapements. The practical escapement is one which has a minimal number of components, can be easily mass-produced, and will attain a high degree of accuracy over a long period of time without attention. This is key if your goal is to design a watch which has an extended service interval. The co-axial escapement is the only escapement in the world today which fits all of these criteria perfectly. And so, onto the power and impulse. I have split this section into two parts, and in part one, we'll take a very quick look at how the power is delivered to the escapement. Over the years, I have come to appreciate that keeping to as few components as possible throughout the whole mechanism is essential in creating energy efficiency. We need to look no further than the Marine Chronometer as a perfect example of efficiency in design, with its basic train layout consisting of barrel, centre, third, fourth, and escape wheel. It is this basic approach which was key to the success of the chronometer. Any components over and above these basic requirements I would consider to be an overcomplication. This approach is commonly used throughout watchmaking today, although with the fast beat and long duration watches, extra wheels and barrels are appearing over and above the basic layout. I propose that this is not a good direction of heading when designing a watch where the goal is an extended service interval, or for that matter, longevity. Let's not forget that power requirements will increase for every additional wheel fitted into a train. And with an increase of power, you increase demands on the lubrication and shorten the service interval. Surprisingly, or is it? Design efficiency is not an approach we hear talked about in watchmaking today. The final thing to consider, where our focus is a smooth and efficient transfer of power through to the escapement, is this. How is the power delivered through to the escapement at the low power end of the train? Here we have the extra flat Daniels co-axial escapement, and this is a good example of a poor transmitter of power. That's due to the large diameter 2.5 to 1 ratio gears. These two mating gears actually create a braking effect. It's due to the engagement between the low ratio gears on such a large diameter. This is further compounded due to their positioning at the low power end of the train. So here we're going to need an increase in mainspring strength to overcome this drain in power. The preferred setup would be to have a ratio of no less than 7 to 1, which would enable free, uninterrupted power delivery and without the braking effect caused by the close, large diameters. It's at this point that alarm bells should be ringing. Why? Because in an escapement which needs more powerful or multiple mainsprings over and above the norm is therefore an inefficient one, and it should be discarded. So how is the impulse delivered? The best way to illustrate this is to show you what happens between the escapement and the oscillator. Here on the left, we have the commonly used lever escapement. The delivery of impulse is through a sliding action. And on the right, we have George's remarkable co-axial escapement. Here the impulse is delivered through a simple pushing action. Hold that thought, because I'm going to come back to this difference in more detail. But for now, let's look at the significant energy losses that happen when you combine the sliding action with fast beats. Yes, everyone, we're back to that poor old fast beat escapement, which is getting a proper drubbing this evening. So perhaps we're already creating friction. So remember, we're already creating friction with a lever escapement due to the sliding action. Now, if you increase the escape wheel tooth count from the standard 15 up to 20 teeth, then each time the escape wheel revolves, those 5 extra teeth cause an increase in friction per degree of rotation for that wheel. Again, this is a further loss which will have to be accounted for with a stronger mainspring, and so it should be discounted. And just to recap, over the past 50 years or so, the frequency of the lever escapement has steadily increased from a generally accepted 18,000 vibrations per hour up to 28,800, and in some cases 36,000 vibrations per hour. This is twice the rate. The more teeth that an escape wheel has, the more friction that it will create in each of its revolutions. Increase the rate or vibrations of the watch, and the service intervals increase, which I maintain is a step backwards. A renowned heart surgeon commented to me that small creatures generally have faster heart rates. Animals with faster heart rates have a shorter lifespan. I believe that the same correlation can be made with the fast beat watches, and we should take lessons from the natural world. Now let's look at the detail. On the left, we have the lever escapement. The long red line shows the amount of friction that the escape wheel tooth has to overcome for each tick of the watch. And it's this surface which requires lubrication for the lever to work to the best of its abilities. On the right, the short red line is the amount of friction. And I've put the word friction in inverted commas because any apparent friction is negligible due to the action of pushing in the direction of travel as opposed to the sliding action found in the lever. When explaining the differences in power delivery between the lever and the coaxial escapement, I find there's no better way than to use this man and door sketch. The hand represents the escape wheel tooth, and the door is an impulse jewel. You can all try this at home. To experience the forces required to deliver power through a lever escapement, first place your hand by the hinge side of the door and walk forward, allowing your hand to slide across the door face. In a watch, The friction experienced between your hand and door has to be lubricated in order to reduce its effect. Now for the coaxial. Place your hand by the door catch and walk through the door. The effort is greatly reduced with negligible sliding. Congratulations, you have just experienced the super efficient tangential power delivery found in the coaxial escapement. It should be noted that for a coaxial, the escape wheel is being driven in the direction of travel, and so any apparent sliding friction found in the escapement is converted to more of a pushing action. We have seen the differences between how sliding and pushing impulse occurs. But how does this play out in practice? In this diagram, the green represents the angle at which the escape wheel is involved in the delivery of power through to the balance. A lever escape wheel spends 210 degrees of its rotation involved in the delivery of power. Green represents power. A coaxial escape wheel spends an extra 45 degrees imparting its energy, which means that 255 degrees of its rotation is involved in the delivery of power through to the balance. This is good, and it's a gain over that of the lever. In calculating this, I found that for one revolution of a 4.5 mil diameter lever escape wheel, 9 mil of sliding action takes place. For a coaxial escapement of the same diameter, there is only 1.1 millimeters of negligible sliding action due to the direction of travel. And this is for one revolution of the escape wheel. The rest of the impulse is simple, frictionless pushing action. This is a 10 times efficiency saving for the coaxial over the lever escapement. So for a watchmaker, this is wonderful news, because these savings in energy are something that we can use in order to further enhance the life of the mechanical watch. And again, let's remember that the more teeth an escape wheel has, the more friction it will create for each of its revolutions. So I've talked about many of the pitfalls and qualities to look out for when planning and designing a new watch mechanism. But how do we carry this out in practice? Well, I can only share my experiences from developing the coaxial escapement and my Series 2 movement. It was a 25-year struggle for George to convince the sceptical watch industry that his coaxial invention was superior to the lever escapement. But he succeeded, and in 1999, Omega launched the first industrialized watch fitted with a Daniels coaxial escapement. It has proven a great success. Back in 2004, I began development of my first production wristwatch movement, my Series 2. I was determined that it would be built to a standard way beyond anything mass-produced. I wanted to achieve the same high-quality standard being produced during that original golden age of English watchmaking. This Series 2 also had to house the coaxial escapement, assuring the craft was being met by advanced science. The mechanism also had to hold its own. As George claimed his escapement would extend service intervals up to 10 years, I had to design a strong and rigid mechanism to match that term with uninterrupted power delivery, something that was stronger than anything else found on the market. Where do you begin? Well, in order to create a baseline, I decided to take a mainspring and a balance spring from a vintage Omega 30mm wristwatch caliber. I had always admired this watch mechanism due to its strength of design and reliability. I began designing the mechanism around just those two components. It was a challenge, to say the least. Throughout the design and prototype phase, I had no idea whether the watch would perform as I'd hoped. We worked out a train count for the watch, which had the minimum requirement of wheels and would vibrate at 18,000 vibrations per hour. This would take us back to a frequency demanding less workload and thus extending service intervals. I also increased the scale of the wheels found in the Omega 30mm caliber. I wanted my wheels and pinions to be larger, stronger, and with good sized pivots to withstand the minimum of a decade without attention. The design of the mechanism went well, and next was the escapement. This was no walk in the park either. Firstly, unlike the lever escapement, where we had over 250 years of knowledge to draw on, for the coaxial there was virtually nothing. We had George's designs, but of his 9 coaxial watches, each one had been a prototype. This meant a comparative analysis of the escapements, and their performance was impossible. There were those first production Omega coaxial movements, but the base caliber of these movements was a high beat and originally designed to house the lever escapement. The coaxial escapement had been retrofitted into it. As such, although made in large numbers, I knew that there was little to be gained from this mechanism. My design ethos was already very different to that of the industry, and I wanted my movements to have longevity designed into them. I was also becoming well aware that the power requirements of the coaxial were very different to that of the lever escapement, and so a completely new ground-up design had to be created. Nevertheless, work progressed well, and the prototype was launched in 2006. The Series 2 had the distinction of being the world's first production movement to have been designed around the coaxial escapement. It was also the first ground-up production watch to have been designed since the demise in the 1970s of Smith's watches. No relation. 13 years later, the 100 rwsmithwatches and 35 Daniels anniversary pieces produced by me and my team have all played their part in the continued development of the coaxial escapement. The development of this escapement has been a fascinating process and has informed much of what I'm talking to you about this evening. My very first iteration of the escapement was a 2-wheel setup in 2006, where the geometry was taken directly from the practical watch escapement. It worked, just about. But it was at this point I realised changes would have to be made in order to suit the needs of the watch that I was designing. This was the beginning of a huge development phase, which 13 years later is still ongoing. Early on, I began looking at weight-saving changes that could be made to the lever and the roller. These changes did make marginal improvements to the life of the escapement, However, the first real change came in 2010 when I had one of those light bulb moments in the middle of the night and came up with the idea for the single wheel. I had noticed that some watches were taking far longer to set up the escapement, whereas others were a dream. It was these variations which concerned me. My hunch was that there were concentricity and angular orientation differences between the teeth on the upper wheel and the lower wheels. They were difficult to measure, but I hoped that combining both sets of teeth into a single wheel would guarantee the concentricity and angular orientation of each wheel that we made. It worked. And for the first time in 4 years, I was able to see consistency in results. This consistency gave me the platform to think about further improvements. And that next leap forward came in 2012. Over the previous 2 years, we had been making tweaks to the geometry and construction of the lever and the roller. This improved the efficiency of the escapement's function and was reflected in a reduction of half a mainspring strength. I felt this was a significant improvement, and with this impetus, I began to look at lightening the escape wheel, which I did by 23%. Again, there was a noticeable difference which enabled a further mainspring strength reduction. This was now becoming very exciting, and over the next few years, a new set of previously unseen characteristics began to appear. My feeling was that the escapement as a whole was influencing the balance wheel, which it should not. And so the idea came that surely a reduction in its size would prove this theory. Again, it was difficult to know how much I should scale down the escapement. There's no rule book to the coaxial. All I had was a gut instinct on how small we could go and yet still be able to make it with relative ease. In 2015, the 6mm diameter escape wheel was reduced down to 4.5mm diameter, and the changes were dramatic. So much so that a complete redesign of the Series 2 movement was soon undertaken to house the 4.5mm escapement. So where are we with the coaxial today? Well, I would say that we have finally tamed the beast. Its development is by no means over, but for the first time in its short history, we have managed to pin down its characteristics and to create a set of principles for the escapement. Interestingly, my view of the book, The Practical Watch Escapement, has changed, and I would advise anyone contemplating the use of any of George's escapements to now regard the book as a set of principles to work from. My experience has shown this. The few watches George made to contain his double wheel and coaxial escapements were enough to prove out his theory, but too few to prove out the long-term characteristics. But this should not be a surprise to me, especially when you consider that the lever escapement has gone through 250 years of development since its origin with the British watchmaker Thomas Mudge. Yet the basic principles of Mudge are still there in the escapement today. So how do I gauge our success? The simplest way is through the strength or thickness of a mainspring, which is a power supply of the watch. Since 2006, this has dropped from 0.155 of a mil down to 0.115 of a mil, which is 4 whole strengths. A whole strength, by the way, is 0.01 of a millimeter. In watchmaking, this is an enormous leap. And let me try to put this into perspective. In my former life, as someone servicing watches for a living, I would sometimes get an old and rather tired watch in for service, where the amplitude of the balance was sluggish. An increase in half a strength to the mainspring, or 0.005 of a millimeter, would most likely be enough to revitalise it. And it is this which really puts the efficiency of the coaxial into perspective. 4 whole strengths, or 8 half-strength reductions over the 13-year development of my Series 2 movement is dramatic validation of its superior efficiency. And so the secret to creating a watch with an extended service interval is as follows. You want a low energy demanding escapement, which is not reliant upon a lubricant for it to work efficiently. You also want a well-constructed, sturdy mechanism containing a single mainspring barrel and just 1 train of wheels. These wheels should contain just the basic 5 gears calculated to vibrate the balance wheel at no more than 18,000 vibrations per hour. By using this combination of qualities, you should achieve a watch with a greatly extended service interval, one which is way beyond industry standards. And how does it do this? Well, it's all thanks to the low power requirements of the coaxial escapement. This allows me, as a designer and maker, to create a watch which is far stronger than the industry norm. It is therefore better able to withstand many years of running without attention. That's due to the lower forces running through the components, such as a gear train and winding mechanism. And in turn, this reduces the need for heavier lubricants and also aids in extending the service interval. Since the creation of my first coaxial wristwatch back in 2006, my understanding of the escapement and what it can offer to timekeeping has completely changed. Throughout history, the sole objective of any designer of escapements has been to create a highly accurate timekeeper. I believe that the objective has moved on. It is no longer just about accuracy, but how an escapement can benefit the whole watch with its efficiency and low power. Of course, none of this should have been a surprise to me, because George always championed the coaxial escapement on its extended service intervals. But what my work has done is to prove George's theory. Today, we have extended the service intervals from an initial 7 years up to our predicted 10 to 15 years. It's still early days, however, and dependent on the data we receive from watches out there, I predict the service interval being extended to over 20 years. These figures are unheard of in the watchmaking industry today, but what they demonstrate is this. By focusing research and development into key areas of escapement and movement design, real gains can be made in terms of efficiencies in the mechanism as a whole. That, ladies and gentlemen, is a path I've chosen for the rest of my life's work. Thank you.
So we have some time for questions. There are a couple of microphones here, and there are some student ambassadors who will pick up the microphones and enable them to be passed amongst you. So let's start. So the gentleman here for the first question. Microphone just coming there.
That was fascinating. I really enjoyed that. I'm just wondering if I've understood correctly. You said earlier on that an increase in frequency was a response to the accuracy of watches, which then inherently introduced increased stress on the mechanism and thereby reduced service interval, which you've addressed by developing an escapement which then allows for a reduced frequency. Okay. Does that mean that you're to some extent willing to sacrifice accuracy in order to increase robustness and increase service?
Oh no, definitely not. No. The great thing about the co-axial escapement is that it's not reliant on lubricant, and so you have a far higher degree of accuracy over a far longer period because there's no oil on the escapement to deteriorate and affect the rate of timekeeping. So I heard many years ago that for a lever watch, before it leaves a factory, they always expect the frequency to be, I don't know the correct amplitude or the angle of amplitude for the frequency, but they always expect after 6 months for that amplitude to drop down by about 30-40 degrees. And that's just because the oil has already begun to deteriorate. It then remains static for a few years, but then as soon as the oil begins to thicken, then the rate of timekeeping drops off dramatically. So now we're still improving on the rate of timekeeping over the lever scheme.
Okay. Yes.
Thank you very much indeed. Do you feel that material technology will also play a part in the future?
Not particularly. No, I mean, I think what George did, was to prove that by focusing on the life of the mechanism, you can make dramatic improvements. And our work, to some extent, has also proved that. I think what George would have said about many of the new materials which have come into watchmaking, things like silicon and so on, really, you're not dealing with the problem. The problem is an inefficient mechanism. And by changing the material, an escape wheel, let's say from lever from steel to silicon, is only masking the problem. It's not getting rid of it. So, to date, no.
Yes, the gentleman in the waistcoat in the middle there.
I was just going to ask if you expect your development, or how is your relationship with Amiga now? Do you expect that your developments with this might pass to them or not?
I don't have a relationship with Amiga. So, no, I mean, this, I live in my own little world and I'm just focusing on that. And I know that with Amiga have made changes and they are using different materials and so on, but I don't know how that plays out in performance in the watch. I mean, I'm just not privy to that, unfortunately.
There's another question there in the centre.
Hi, thanks for your lecture. Do you think who's this going to benefit? Would it be more the customer or the watchmaker stroke repairer? And my second question, so I will throw one in there. Why, if there's a 10 to 15 year service interval because of the coaxial escapement, don't you think that there's going to have to be a better development of oils and greases to keep up with that? Because there's usually a six-year lifespan of these oils, and then with the degradation of those oils that are happening.
Well, yes, you could say so. I mean, a lot of what I base my work on is the experience of these lever escapements, these brilliant Amiga movements from the 1950s and 60s, where one of those, you could get in and it had been running for 15 years, 20 years without service. They were 18,000 vibrations per hour. They still ticked very happily, even though most of the oil in the watch had disappeared. And when I designed my watch, I designed them with that in mind. So if we do get a watch back for service in 15, 20 years' time, I expect the oil will have gone, but it'll still be ticking away happily. So, yeah, I don't know. But we are working on other things to try and replace oil. So that's another sort of area of my work.
Okay, to be fair, I'll take a question from this side of the house.
Your coaxial escapement is designed to run dry, yet I believe that the Omega coaxial escapement needs lubricant. Could you comment on that, please? Yeah, well, actually, we do put a bit of lubrication on the escape wheel as well. So what we found, when I was working with George, we found that if you left the escapements dry, you get a build-up of deposit where the tooth hit the jewel. So we used a very fine oil, which was almost absorbed, we think, by the steel. And that just prevented this oxidation build-up. And George always put this down to the modern stringent cleaning methods that are used, which are industrial, and they really will strip away any oils that you may find in the materials. So I've continued with this, mainly out of fear, because I don't want any returns. Again, this demonstrates, we use a very fine oil, what this demonstrates is that as the oil deteriorates, it doesn't affect the rate of timekeeping, whereas in a lever it does. And a good example of this is we had a client contact us about a year ago, and he has two watches. He has a Daniels and he has a Series 2, and he alternates 6 months on, 6 months off. And his Series 2 wristwatch was still keeping the same rate of timekeeping as when it left our workshop 10 years previously. And that's extraordinary. And what I noticed, what sort of spurred this on, this sort of presentation, was that we never get watches back through want of a service. We have had watches back due to design issues on my behalf, or a fault with the build of the watch, but never through want of a service. And that is what really got me interested in starting focusing on where we're at.
Okay, and let's take the gentleman with the yellowish shirt top there.
With the general business side of servicing as is for the mainstream, do you think this is something that's going to be taken on with relish by larger companies with the amount of money that they're making out of the larger sales?
No, not at all. No. I mean, look, I'm just plowing my own little furrow and enjoying myself as I go along. And my interest is the improvements of the mechanical timekeeper. And one thing that has always been a potential concern is the service department. In the workshop that I run, and those are costly and they take away from making watches. So, again, this is, hopefully we'll never have to get there. But no,
the industry is doing its own thing and making great watches, but yeah, it's a different world to mine.
Okay, we're running a little bit out of time, but let's have a question from the front.
Thank you. In his book, George described his rather unique marketing strategy where he would pick people, tell them he's making a watch for them, and they would be forced to buy it or they would reflect pleasure. How do you select your customers?
I wish I could be so choosy, but no, I mean, it's very different. George made one watch per year. I have a business, many mouths to feed. And, no, it's interesting. It's people just contact us, email and order a watch. It's very, very easy. And we say yes.
I like that. The gentleman on the stairs there, I think.
Hi, thank you for the talk. I have a two-part question, if I'm allowed. The first one is going back to materiality. I'm not sure that you're aware of the Panerai Lab ID, which promises a 50-year service interval due to that materiality. What are your thoughts going on that? And the second question is, what do you think the evolution of your co-axial movement will look like in the future? Do you have any plans? And could you give us a little bit of insight on that? Thank you.
Yes, I'm unsure about this, the dial. I think I know what you mean, that vibrates at very high frequency. Again, that's using modern materials. And I've never really understood modern materials because, you can go to auction today, buy a pocket watch, which is 200, 300, 400 years old, with very, very, minimal work. That watch will keep as good a time as when it's first made. And I think that's testament to, the fact that making watches from traditional materials is, it's perfect. It does the job. For a second part of your question.
It's basically the evolution of the
co-axial. Yes, so, the co-axial is, we've been working on it now for 13 years. I use the lever escapement, which has gone through 250 years of development, and I'm sure, Amiga will continue to develop the coaxial as we are. I don't think in 100, 200 years' time, I don't think it'll be vastly different at all from George's initial concepts. But what it will have done is changed, perhaps geometrically, and we're still looking at tweaking the geometry to suit our needs. But that's probably more on a watch-to-watch basis, really.
I think we've just about run out of time, but if you permit me one question, and that is, you said that as one of the things that you did was waking up in the middle of the night with, this is the design. I wonder, do you see any role for computer-aided design in perhaps trying to optimize some of these new designs that you're considering to give extra longevity, I suppose, of between services or precision or whatever?
There's no doubt about it, and I think that's the way industry does work. It's, we use SolidWorks. In fact, we're just learning how to use SolidWorks. We're going through a big learning curve, and I believe that can tell you the efficiencies and power requirements of a mechanism or whatever you're building. For me, though, it really is experience. It's practical experience at the bench. Everything I've talked to you about tonight has been practical. It's all gained from practical experience. And I remember Georgie came back from Switzerland. He'd been at Amiga, and they were having problems with the coaxial escapement in the development phase. And we'd been examining these mechanisms which had been coming in from Amiga because we were going to build a series of watches out of the early pieces. And we noticed that 3 of the 8 escape wheel teeth missed the jewelry. And with every single watch, there's obviously some eccentricity issues occurring in the assembly of these two components. And so George got on a plane, went out to Switzerland, and he said, okay, this is the problem. And they said, oh no, but there isn't a problem. There is not a problem. And they took them into their lab where they had the computers and the screens, and they demonstrated on the screen by, manipulating the components that what he was talking about was not true. So George said, well, do you have a comparator? And a comparator is a device which magnifies your components onto a big projector screen. And they took some time to track one down, but in the end, they did find one at the end of a very long, dark corridor, and George put the watch on there, and he fed through the escapement. Sure enough, 3 of the teeth missed the locking jewel. And that's the difference. You can't beat the practical experience. And that's something that I know, trust, and will carry on.
Okay, I think that's an excellent note on which to finish. I think before we invite you to come and join us for a glass of wine and something to eat, I think on your behalf, I'm sure you'd like me to thank Roger for an absolutely fascinating lecture and for taking the time to respond to a wide range of questions this evening. I think it shows very much that the tradition of George Daniels and his role as a mentor and so on has proved to continue in the work that Roger is doing. So there is a wonderful audience here. I think you have the invitation just to email your order in. So, or you can have a chat over a glass of wine. So let me ask you to thank Roger again for a fascinating lecture.